Okay, so R indexing Wheeler graphs. So this talk is I'm not planning to send this somewhere else, but it was something that came up in a paper that we were working on. It's a generalization of something we needed for that. Carlos will present that later. So what are Wheeler graphs? Those were presented. Giovanni gave an invited talk at CPM a few years ago when we came up. So a Wheeler graph is a directed edge-labeled graph whose vertices can be ordered such that those with in-degree 0 precede those with positive in-degree, and for any pair of edges E U V and E prime U prime V prime labeled A and A prime respectively. If the edge label A is lexicographically smaller than the edge label A prime, then the destination of the first edge has to be earlier in the order than the destination of the second edge. This is going to turn out like we came up with Wheeler graphs because we said we're generalizing Boris-Wheeler transforms to different kinds of data, and we're always proving the same kind of thing. What's the underlying what's sort of the underlying concept? And so there's this idea of if you have an edge, edges with smaller labels go earlier in the order than edges with larger labels, and then if two edges have the same label, then the order of the edges' destinations is the same as the order of their origins. Okay, so here's an example of a Wheeler graph. And here's the Wheeler order that shows that this is a total order on the vertices, such that, so it's not the only one. I think you could switch 7 and 8, for example, but this order works. How can you see that this is a Wheeler graph? Oh, well, okay, why do we care about Wheeler graphs? So if G is a Wheeler graph, and we store a ranked data structure over its edge labels ordered by their origins, and partial sum data structure over the vertices in and out degrees, then later, given a pattern P in length of P log size of G time, we can find the interval in the Wheeler order containing vertices reachable by paths labeled in P. So this means if you consider the language of this graph to be the strings that label walks on that graph, then we can construct a compact and fast index for that language. So how do you do this? So you take this. Can people see my cursor? Anybody? Maybe. No. That's going to be difficult.
Yes, we do.
Okay, so you do see the cursor. Okay, because it's not important here, but it will be important later.
No, okay, no, that's perfectly fine.
Okay, so so if you take this, you take this order on the vertices such that the first vertex with in degree 0 has it's first in the order. It's 0, and then everything else, the things with incoming edges labeled A are earlier in the order. So this is a generalization of sort of suffix arrays. So this has the lexicographically smallest path. If you look here, it's an A, and then it's a C, and nothing else has a path labeled something smaller than AC coming into it. So this is 1, AG, this is 2. So if you put these the vertices and you write the labels on their out edges, this corresponds to a Boris-Wheeler transform. And then of course the labels on the in edges are just sorted. So there's no in edge, and then a bunch of A's, a C, a G, and a bunch of T's. How does this index work? Well, from the Boris-Wheeler transform, you can actually get this graph back. From the Boris-Wheeler transform in the in and out degrees, you can get the graph back, because if you look, the A's all have to go to vertices that are together in the A part of the interval. And the C has to, well, there's only one C, so it goes after the A, and then the G has to go after the C, and then the T's all have to go together. So the key idea is, if you look at these arrows, when you look at them all together, it's a mess, but if you look at them sorted, separated by characters, these lines don't cross. So if you know this is the third out edge labeled T, it has to be the third in edge labeled T. And because it's easy to store what the in edges are because they're sorted, okay, then so you can rebuild this. So it's the same kind of thing that we've been doing for ages and ages with Burrs-Wheeler transforms based data structures. So the mnemonic for this is, remember that crossing these edges don't cross. The streams, no crossing the streams. So in the next talk, Nicola Cotomacho will tell you about how you can cross the streams a little bit, but for this talk, no crossing the streams. So just as a quick example, keeping track of the time here, as a quick example, how would we find the vertices that can be reached by paths labeled TA? Well, the first thing is all of the vertices can be reached by paths labeled empty. And so from here, we can say, okay, from this interval of all the active nodes, we consider all the things that can be reached with T. So they're the interval here from 6 to 9. And so these are the vertices that can be reached by edges labeled T. And then from there, where are the edges that labeled A leaving this interval? Well, they go here. So the only vertex that can be reached by TA is 3. And it can actually be reached two ways, TA and TA. Okay. R indexing. So this is from a paper a couple of years ago. Let S be a string and let R be the number of runs in a BWT of S. We can store S in O of R space such that where R is the number of runs in BWT, in O of R space such that later, given a pattern P in P log length of S time, we can find the interval in the BWT containing characters preceding occurrences of P and S, and then report the locations of those occurrences in log S time per occurrence, length of S. So the key thing is being able to report the locations of the occurrences fast. So I won't go into too much detail about how this works. Also, Nishimoto and Tabe sped this up so that now they can get optimal length of P plus awk time when the alphabet size is polylogarithmic in the length of S. Just really quickly saying how this works. What you're going to do is at the run boundaries in the BWT, you store pointer. You store sort of the suffix array, the position of the in this case, the successor. Okay, so if you look at 33 and 34, why is there an arrow here? Because the 33rd character is a C and the 34th character is a G. They don't match. They're a run boundary, so we store a pointer from 33 to 34. 37, the 37th character is a G. The 38th character is a T, so we have a pointer. Why don't we have a pointer here? Because the 50th character is a C, the 51st character is also a C. So these aren't all the pointers you would store, they're just all the ones I need for this demonstration, and actually they're a fair fraction of the pointers that you would store at the run boundaries. So using the magic of something called the toehold lemma that we didn't do, so if you want to know about it, it's Polykriti and Pretza, you can find the lexicographically first occurrence, the first prefix, first prefix that ends in TA. So you find this one. So now it would be cheating for me to show you how to find the other ones, using with all of this information written here. So let's make that go away and let's see how this works. So we found this red circle. How do we find the other occurrences of TA? Well, I'm going to follow this line until I hit one of these dashed pointers. Okay, and I'm going to keep track of how many steps that are. Now, I'm not actually going to do that step by step. You do this with a successor data structure. So it's 2 I follow the pointer, and then I go back 2. So this is also an occurrence. Now here I follow to here, which is 11 steps. I draw, I follow the pointer, and then I go back 11. So this is also an occurrence. Here I follow here, which is 5, and then I go follow this pointer, and then I go 1, 2, 3, 4, 5. That's an occurrence. Here I follow to here, which I don't know how many steps that is. I drop down, I go back. That's an occurrence. Here I go to here, which is 2 steps. I follow the pointer, and then I go back to 2 steps. That's an occurrence. Here I go to here, which is 1, 2, 3, 4, 5. I drop down, and then 1, 2, 3, 4, 5. That's an occurrence. Here, 0 steps. I go to here. That's an occurrence. I follow the pointer, 0 steps. That's an occurrence. I follow the pointer, 0 steps. That's an occurrence. That's 0 steps. That's an occurrence. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's an occurrence. And now I found them all. Okay? How does that work? It's magic, and I don't have time to explain it. Okay, so why would you want to put these things together? What is the result? So this is, let G be a Wheeler graph, and let R be the number of runs in the Burroughs-Wheeler transform of G. Suppose G can be decomposed into upsilon edge disjoint directed paths whose internal vertices each have in and out degree exactly 1. These are unitigs, okay? So upsilon for unitig. We can store G in O of R plus upsilon space such that later, given a pattern P, in length of P log G time, we can count the vertices of G reachable by directed paths labeled P, and then we can report them in log size of G time per vertex. So this isn't actually that hard. We're just we're taking the unitigs and we're treating them, the upsilon unitigs, and we're treating them as like strings. So it might be interesting. I don't know if you can use Nishimoto and Tabe's technique to get a speed up here too. When the alphabet is polylogarithmic in G. Okay, so how do you remember this? It's upsilon is the number of unitigs, and I tend to say oops a lot. So we needed this for a special case of this for a paper in a theorem in a recent paper Garance will present later about long and stringy trees. It's actually easy to prove the general theorem, more so than to explain why we want it. Wheeler graphs are cool, R indexes are cool, so R indexing Wheeler graphs is really cool. Yoni Siran actually says he's implemented something like this, so it may be useful for something. And Nicola Preza has a more sophisticated result in the Soda 21 paper about trees. Not sure that's practical. So I want to talk about tunneling, which isn't my idea. It's from Uwe Bayer. Uwe introduced tunneling to reduce the number of times we need to write large run lengths in a run length compressed Burroughs-Wheeler transform. We can put paths in a Wheeler graph together in a tunnel. So you're going to take a Wheeler graph and now you're going to squish it. So you can take 2 paths and you can squish them together if the corresponding edge labels match and the corresponding vertices ranks are incrementing in that Wheeler order. And you do this, but you stop 1 edge earlier than you would think. So let's see an example. How did I get this graph? Well, I merged these 2 paths. And you can't merge this bit because it's different, but you can merge these vertices and these vertices and these vertices, and then you stop 1 edge earlier than you think, and then you can merge these vertices and these vertices, these vertices and these vertices. Okay? So here's a more complicated example. So you notice that this stuff is similar. 0, 1, 2, 3, 4, 17, 18, 19, 20, 21. Now, and then over here, this doesn't look, it's 49, 45. That doesn't look, but it's 45, 46, 47, 48, 49. So you can merge them. 8, 9, 10, 11, 12. You can merge them. Okay, so what do? You identify these blocks and you stop 1 edge before you think you would. So these are all C's, these are all A's, these are consecutive, but you don't do that because that would be the last step. So you merge them like this. Now why do you leave this last step and you don't go as far as you can? Because these edge labels are all the same, so the order of these vertices, these edge labels are the same, the tunnel labels are the same, so the order here is the same as the order here, 5, 1, 2, 3, 4. Whereas if you look at the order here, it's a different order, because these edges don't match. So the idea is, this edge, this is 5th when you go into the tunnel, so it's 5th when you come out of the tunnel. So the lexicographically largest thing going in is the lexicographically largest thing coming out. Okay, so it preserves the ranks. So you're not actually losing information or changing the language of the graph when you do this compression. So you can index a tunneled Wheeler graph so as to prevent false positive chimeric matches, which are bad, maybe. So in our example, if the first variation is CAT, the second variation isn't TC, and maybe you don't want to include things with CAT and TC in your index, because maybe if you have CAT, then if you have TC, it will kill you. So if you didn't observe a pair of variations together anywhere in your index population, you don't want your index to match that. And you can, like if you do filters and colors and stuff like that, you can get rid of it later, but this means you can't get nice bounds, so maybe you just don't want your index to return that anyway. Okay, how do you remember how this works? I found out while doing these slides that this is called a loom tube. So just think of the tunnels as the tubing for your wires, your loom tubes, and tunnels are FIFO, first in, first out. Now, in this case, it's lexicographically first in, it's lexicographically first out. Okay, so why do you want this? So here's, why would you want to R-index a tunneled Wheeler graph? Because the tunneling takes advantage of the repetitive structure, so it already collapses the runs. So wouldn't a standard sampling be better? So if you're already trying to take advantage of the runs, of the repetitiveness when you're tunneling, can you then try to take advantage of it again for R indexing? So I was thinking, suppose the conserved regions between variation sites are on the order of 1,000 base pairs, and the probability of a base pair mutating is on the order of 1 in 100 million. So I'm not sure about that. So you can read the footnote. I think it might actually be smaller than the probability might be higher than that. And suppose we're indexing 1 million genomes. So this is pure speculation. We'd like to tunnel the conserved regions, but how do we deal with the mutations? Well, people tend to sort of want to filter out the mutations, but I've seen this in a movie where people try to get rid of the mutations, and it doesn't end well for them. So we shouldn't do that. The conserved regions of about 1,000 base pairs are going to be broken up in expectation by about 10 mutations each. So if we merge the paths in the conserved regions into about 10 tunnels, then we should still get a significantly smaller, interesting Wheeler graph, but the Burroughs-Wheeler transform is still going to be run length compressible. So I was supposed to finish at 11:40 my time. Happy year of the ox. Happy belated birthday to Moni, who you heard about a little bit in Dominic's talk this morning. And are there any questions?
Yes, thanks again for the talk. And